we'll get started. This will be the last lecture for transmission lines. Okay, so we'll try to wrap up, but we'll wrap it up with a few questions. Okay, so the questions will be open, and then you can think about it when you have time. All right, because there has to be a motivation for you to study further about these. So I will open up a couple of questions and then allow you to think over a period of time. All right, as to what can happen. So the first thing I'll do is pick up where we stopped in the last class in the demonstration. Okay, we looked through the data sheets of different cables. Okay, and I'm picking up some value from the data sheets of these cables, and I would like to do a couple of calculations. All right, to just highlight to you where we are headed. Okay, so I'm going to start with a problem. Okay, so for a transmission line, in this case we used coaxial cables. Okay, we had the value, this I have taken from one of the specifications sheets, right. Seems rather high. Okay, L was 0.2 microhenries per meter, capacitance the order of 10 picofarads per meter, G is 0.02. Please note that this is just one of the cables that I took. It seems to be a particularly poor cable, or the frequencies at which these data have been taken are quite high. Okay, but it serves a specific purpose for this lecture, so I have picked these values. So I have R, L, G and C. Okay. So there are two things that one can immediately calculate. One is going to be the characteristic impedance. You could do square root of R plus j omega L divided by G plus j omega C, and you will get Z naught. But let us now go ahead and try and see whether we can calculate complex propagation constant. Okay. So I want to calculate complex propagation constant. Okay. I want to calculate complex propagation constant gamma, and I know that from our previous lectures gamma is given by square root of R plus j omega L times G plus j omega C. Another way to remember this, which will be useful for the later part, right, is square root of series impedance multiplied by parallel admittance of your equivalent circuit. So in this case R and L will be in series, G and C will be in parallel. This is another way to remember. Okay. Means that in order to calculate gamma, I need to have idea about one more parameter, which is omega. Okay. I need to know the omega values for calculating gamma. Right. We can start with a very simple case. Suppose we assume that R, L, G and C are going to be frequency independent. You can make a simple assumption, okay, just to see what happens, right. And we can try and see what is the value of the complex propagation constant for different frequencies. Okay. So we can start with a low frequency, say 1 megahertz. So the experiments that we conducted in the demo session were at 100 megahertz, but we are starting just at 1 megahertz. Okay. Okay. At 1 megahertz frequency, I will be having square root of 0.1 plus j omega is 2 pi into 1 megahertz. Okay. multiplied by the value of L. L in this case is 0.2 microhenries per meter. Okay. Okay, times G plus J omega C. Value of G that we have is 0.02 mho per meter or 0.02 Siemens per meter, okay, plus J times into the value of the capacitance per unit length, that is in this case 10 picofarad. Okay. So, you have R plus j omega L times G plus j omega C. It is a big number, you can make some calculations, alright. I have made this calculation and I noticed that the value of the complex propagation constant is coming out to be 0.117 plus j 0.108 per meter. Okay. Okay. Here we already know that the form of gamma that we have is the real part is going to be your attenuation constant alpha and the imaginary part is going to be your phase constant beta. Okay. So, you are ending up with some value of attenuation constant which is 0.117. Okay. Now, let us find out the propagation constant at 1 gigahertz. Now, we keep all the parameters fixed, assuming that all the parameters are fixed. It is an assumption, in practice it may not be so, right. But assuming that all your R, L, G, C are going to be frequency independent and I just change the frequency, I will have gamma is square root of R plus j omega L times G plus j omega C. I immediately notice that omega is present in the numerator, which means that I am going to be having higher values of omega plugged into this equation. As a consequence, I should expect that my alpha values are going to be higher. Okay. I do not want to substitute once again, can substitute, and the value that I have is 1.4 plus j 9 per meter. Once again, the real part is alpha and this is the phase constant. Okay. The first thing that we notice that in the transmission line, for a lower frequency, the attenuation constant is very low. For high frequency in the same transmission line, assuming all the parameters are fixed, the attenuation constant is very high, which is consistent with the data sheet that we were seeing for the cables. However, I have just picked one of the poorer cables at a particularly bad frequency, but nevertheless, the tendency is gamma is going to be equal to square root of R plus j omega times G plus j omega C. Any increase in gamma invariably is going to drive your alpha, okay. Which means that for higher frequencies, the question becomes, is a wired transmission line approach suitable or not? Okay. Because as your bandwidth requirement will keep increasing for communication, you will notice that the transmission line, which has a forward and a return path consisting of wires, will invariably end up having higher and higher amounts of attenuation. This is something that you cannot deal with easily. The only way to deal with this in practice is probably build better cables. This is one approach. The other approach is have some amplification in your lines. For example, when your signal deteriorates over a distance, at that distance keep some kind of an amplifier which converts, say, electrical energy and transfers it to the signal. So, you have higher magnitude of the signal that is traveling. So, you will be having in some way some repeating amplifiers of some kind in your transmission line. Okay. But suppose you want to go to extremely high frequencies or extremely high bandwidths, then the approach of transmission lines is going to be questionable at best. Okay. So, we already noticed that even with some practical values, gigahertz frequency operations are already very, very tough in wired cables based transmission lines. Okay. This is the first thing, and just to give you a feeling, we moved from 1 gigahertz to 1 megahertz, okay. I mean 1 megahertz to 1 gigahertz, okay. That is about 1000 times increase in frequency, right. And we could also do the other thing, right. We can, from this we could always calculate the ratio of the propagation lengths, okay. Okay. So, we can say that L 1 megahertz is the propagation length at 1 megahertz divided by L at 1 gigahertz, right, can be calculated. You can just take the real part of your propagation constant. So, you can do 1 by alpha for the numerator for 1 megahertz, 1 by alpha for the denominator for 1 gigahertz. So, you will be having 1 divided by 0.117, the whole thing divided by 1 divided by 1.4. This is going to be your ratio. Let us say it is approximately, I can see that it is 11 or 12 times now. Okay. So, the propagation length at a megahertz for this particular transmission line is about 11 to 12 times higher than the propagation length at 1 gigahertz, which means that at higher frequencies you will need to have amplification much more closer placed to each other. So, if you want to have some repeaters or amplifiers placed periodically on your transmission line, at higher frequencies they have to be closer to each other to provide the same power output. So, this is one direction of thought. As your bandwidth requirement increases or at higher frequencies, how does one start doing communication and how does the theory change? This is the broad question. Okay. So, this is the direction in which we are heading. So, the direction that we are heading towards is there a need to use only currents and voltages, or can you make use of electromagnetic fields? Okay. And in case we end up using electromagnetic fields, because they can travel at the speed of light in vacuum, okay, and they can travel over enormous distances even in vacuum. Okay. If we were to use electromagnetic fields, then is there a considerable change in the theory that we have already learnt? Okay. This is the question, and the broad answer to that is no, there is no change in the theory. Okay. Now, in the next few lectures, we will be starting with Maxwell's equations, because that will be the starting point for this course. The derivation of Maxwell's equations, the Gauss's law, Ampere's, Faraday's law should have been covered earlier in your undergraduate, in your second semester, etc. But here we are beginning with where you left, Maxwell's equations, right. Now, if I try to use Maxwell's equations and try to find the solutions to the Maxwell's equations, is there a similarity that I notice between transmission lines and Maxwell's equations? Can I use similar computer programs to solve Maxwell's equations? Do the RLGC have equivalent in Maxwell's equations? The propagation constant, is it going to be similar in Maxwell's equations? These are the broad questions, all right, and the answer to that is everything is a transmission line. Okay, and the philosophy is everything is a transmission line, irrespective of whether you use wires or not. The only thing that matters is whether you are going to be using voltages and currents or electromagnetic fields, but once you make the switch, I will show that they become nearly identical. Okay. There are a few quirks to electromagnetic fields, right, but other than that, you will see that the vast majority of the theory remains same. So, if you understood transmission lines very well, chances that you will understand Maxwell's equations well is very high. Okay. So, this is one aspect, one direction in which we are going. Okay. I will also pose a question, because now we are wrapping up transmission lines. I will also pose a question for you to think about slowly. Okay. This need not happen during the semester, it can be during your semester break or it can be any other time. All right. One of the things that we had earlier learnt or begun with in transmission lines is the circuit model of a section of a transmission line, and we drew a series inductor for a lossless section, okay, and we had a parallel capacitor. All right, and then we had j omega L to be the series impedance, right, and your parallel admittance is again j omega C. This is what we had before. All right, from here we could always find out gamma to be equal to square root of z times y, and in this case it is j omega square root L C. This is something that we have already seen. Okay. In this case, since gamma is having only an imaginary part, you have only a phase constant, you do not have any attenuation constant, which is consistent with the model, you do not have any R and G. This was the most ideal circuit representation of a section of a lossless transmission line. Okay. In this case, one can go ahead and write, which implies there is only beta. Beta is omega square root L C, right. And we also know that the velocity, okay, thus far we have used the term velocity. The more correct term that I had mentioned in one of the lectures is phase velocity, right, is omega divided by beta. So, omega will have the units of radians per meter, beta will have radians per second. So, we will end up having meters per second, but this is the phase velocity, and we already know that this velocity is 1 by square root L C. Okay. These are some things that we are already aware of, should be on our fingertips by now. Okay. But let us twist the problem very little, all right. Let us just say that I am going to be having an equivalent circuit, but the components are wrongly placed. Okay. The components are switched, okay. They could be switched by accident or they could be deliberately switched, all right, because it is a model, we can plug in anything and try to solve for the voltages and currents. Okay. Now, suppose I have switched the position of the capacitor and the inductor. Okay. Let us see what could happen. First of all, the series impedance, okay, Z will become 1 by j omega C. The parallel admittance will become 1 by j omega L. Okay. This is the first thing that we notice. Okay. The next thing that we could do, just a repeat of whatever we did for the original transmission line, is we could calculate the complex propagation constant gamma square root Z y. All right. This becomes 1 by j omega square root L C, or this is minus j by omega square root L C. Just by looking at it, one may not figure out many things, right. For now, let us just look at it as omega is minus j divided by omega square root L C. I just did square root of Z y, I am getting a value for the propagation constant. But then I can say that the propagation constant is made up of an alpha and a beta, and I do not have an alpha here because I do not have resistors, right. So, this means I have only an imaginary part, which means my phase constant, right, is going to look like minus 1 divided by omega square root L C. Okay. The phase constant looks negative. Okay. We still do not know what to make out from this, all right. But there is one more step that we did before, we calculated the phase velocity. Okay. Maybe we will calculate that also and see what happens, all right. So, we can say that the phase velocity is omega divided by beta, and we can say that this is going to be omega divided by minus 1 by omega square root L C, and this becomes minus omega square root L C. Remember, all we did was just switch the position of the components, and then you end up with something very ridiculously complicated. What happens here is the phase velocity looks negative. This is the first thing that we notice compared to prior result that we have. On top of that, the phase velocity depends on the square of the frequency. That means for different frequencies you are getting different different velocities, phase velocities. Okay. Now, one can also ask a question, does it make any physical sense if your phase velocity is negative? Does it mean that information is going from source to sink? Does it mean that it is going from sink to source? All these questions will start coming into the mind. I just wanted to sow the seeds at the time I am wrapping up transmission lines. Okay. All I have done is switch the positions of L and C, and you can already see that some things big are happening over here. Okay. So, I will stop here. I will allow you to think for the remaining time when you have. Right. So, this may look absurd, okay, but it actually has some deep physical consequences, and what these are known as are metamaterials. Okay. Some things which exhibit some weird properties. So, negative phase velocity, but positive group velocity, negative phase constant, okay, etc. So, in the simplest terms, these are metamaterials. So, since I am wrapping up transmission line, I just wanted to put a word that this is not the end. You can always fiddle with the model and arrive at some something big and also start analysis. Okay. So, you can go back, you can see about these, you can also see what is phase velocity and what is the group velocity, does the information travel from source to sink, does it appear to be reversed, all these things. So, these questions should be there in your mind. So, that is the whole point of putting this. Okay. So, now that I have completely wrapped transmission lines, right, with a big question, I will proceed to wireless systems, all right, or wireless power transfer involving Maxwell's equations. So, the broad topics that we are going to be seeing till the next quiz is Maxwell's equations, solutions to the Maxwell's equations and plane waves, and we will also be talking about interfaces. These are the three things that we will be seeing prior to the next quiz. Okay. Now, I am not going to go into the derivation of the Maxwell's equations. This is something that should have been done much before this course. Okay. So, I am going to start with the Maxwell's equations, and I am just going to revise a few things, and then I am going to proceed to make the analogy with transmission lines. Okay. So, I will start with writing down the Maxwell's equations. Okay. So, I have the Gauss's law, del dot D is equal to rho, right. Depending upon the sign of the rho, okay, I could have fields emanating from charges. So, rho is the charge density, okay. Some convention is followed, plus means that I am having fields diverging out, and minus means that I have fields converging in. Okay. It is the convention that we follow. So, this is the Gauss's law. It just says that the divergence is going to be proportional to the charge density, that is it. Okay. So, higher the charge density, more diverging out your fields are going to be from that point, or more converging they are going to be. Okay. Now, the other Gauss's law for magnetics is del dot B is equal to 0. Since there are no magnetic monopoles, you do not have diverging magnetic fields. This means that your magnetic fields are going to be in the form of loops. So, the divergence is implicitly 0. This is the other Gauss's law. Okay. Now, when we are writing these, all right, I will write down the remaining equations and talk to you about the quirks involved in these equations. I also have the two curl equations, right. Just make it del cross E. Okay. Minus del B del T, okay. And I have another curl equation okay. So, I have written the Maxwell's equations. There are two curl equations and the two Gauss's law. Okay. Now, if I look at these equations, there are only two equations that talk about the coupling between the electric and the magnetic fields. Those are the two curl equations. Okay. So, on one side you are having E, on the other side you are having B, but in order to be clear we have to define what is this D and B also, because those are appearing over here. So, to give the constituent relationships, we can say that B is equal to mu H and D is equal to epsilon E, where epsilon is the permittivity, okay, and the unit is farad per meter. Now, already you should be able to figure out where we are going. Right? The unit is farad per meter. Okay. It has the same unit as the distributed capacitance in the model of your transmission line. Mu has the unit of Henry per meter. It is the distributed inductance. Okay. E has the unit of volt per meter, okay. And H has the unit of amperes per meter. Okay. I think some similarity should be clear. I think we are getting there, all right. Now, there are some quirks in the way we have written the equation and we have to sort it out before proceeding further. In the two curl equations on the right hand side, I have used time derivatives. Okay. I have written these equations in time domain. Okay. I have written these Maxwell's equations in time domain because I have used time derivatives on the right side. So, I want to be very clear about it. Okay. If I am writing the derivatives in time domain, means that my electric field is changing with respect to time, all right. Remember that in your telegrapher's equations for transmission line, you had dou V dou T, you had dou I dou T, all right. You were considering voltages and currents changing with respect to time. Here similarly electric and magnetic fields are changing with respect to time and you want to represent it accurately. That means the first equation has to be written as del dot D of T, okay, is going to be equal to rho of T. You have to be very careful about this. Okay. At some instant of time you are calculating the divergence, at that instant of time you can calculate the charge density. Okay. Del dot B of T, at any point in time you are going to be having magnetic fields which are in loops. Okay. Del cross E of T is going to be minus dou B of T dou T. Del cross H of T is going to be J of T plus, and just to be clear, this is conduction current density. If your rho of T is non-zero, you can have J of T. Rho means you have some charge density. If there are no charges, there is nothing for it to conduct. So, you will be having 0 conduction current density. So, J depends directly on rho, okay. And dou D dou T is your displacement current density. Okay. Now, we have changed all these to time domain, but then we have to look at the characteristic equations, I mean, or the expressions for displacements and the fields also. Right. Now, we have to look at it in a more objective way. B is equal to mu h. It's a very, very tricky thing. D is equal to epsilon E is a very tricky expression to write. Okay. Now, let's now be very consistent and say that B of t is what we are writing down and D of t is what we are writing down. Okay. On the right side I have h of t and I have E of t. Okay. Okay. Now, here once again the correct way to do this is not by multiplication. One of the things that we have to now understand is just like L, C, R and G. Here we are not having R and G yet, okay, we are having rho and J, but we will come to that later. Suppose we start with electromagnetic fields in some lossless medium. The lossless medium will just have epsilon and mu. Okay. But one of the things that we know now have to graduate, right? Previously we used a fixed value of R, L, G, C to calculate propagation constants. But in reality R, L, G, C will all depend on frequencies. Similarly, mu and epsilon should also depend on frequencies. If they depend on frequencies, we have to write this correctly as mu of t epsilon of t, okay, because time and frequency share a Fourier transform relationship. You will have to be very clear and say that it is mu of t and epsilon of t, but there is another quirk. B is equal to mu h usually is written in the frequency domain, okay, and D is equal to epsilon E is written also in the frequency domain. And when you go from multiplication in one domain and you take a Fourier transform, you have to represent this as a convolution, all right. So, the correct way to write this is actually a convolution, all right. So, you see now we are getting into more details than in transmission lines and that is how it is going to be. Okay. So, we started with the Maxwell's equations, right. We have written them in time domain and then we have written the constituent relationships for B and D in time domain, all right. If mu and epsilon are going to be frequency dependent, then the correct way of writing Maxwell's equations with the constituent relationships is actually using a convolution operator for D and E. This is the first thing that you have to remember, all right. Now, this also tells you a lot of things about what can happen, all right. Since we are not talking about only wires, we are talking about big media, we are talking about bulk media, etc., right, and anything will have some epsilon and mu, right. For example, vacuum, which is defined as absence of anything technically, still has epsilon, right. It has the epsilon of 8.854 times 10 to the negative 12 farad per meter, okay. And again vacuum, which does not have anything, has some mu, which is permeability is 4 pi times 10 to the negative 7, right. It means that these are properties of the material at all points in space. At every instant of time you can figure out what are the fields, okay. So, these are some really distributed parameters, okay, over large areas of space, and even in vacuum these things do not become 0, okay. So, this will have some lots of questions, but I think you can think about this in varieties of ways. The first thoughts that we can have about are what are these kinds of materials that we can have. Now, we are dealing with materials because we are dealing with infinitely large media where you can have electromagnetic fields, where you can have mu and epsilon, all right, even in vacuum. What other kinds of materials could you have? So, we will start with these constituent relationships and try to identify the kinds of materials you can have, okay. The simplest kind of material that you can have are known as isotropic media. Okay. Now, isotropic media means that you have the same value of epsilon and mu in all directions. Now you see what happened. Previously we had introduced time. Now we are introducing space into the material parameters. Now what happened is RLGC are not only a function of frequency, but also are becoming a function of position. Okay. So this needs some deeper thought, because previously this direction is something that we didn't consider very intensely, because we know that the direction of the wire is going to be this direction of the transfer of voltage or current, etc. But now we don't have any wire. All right. That means we have to consider in all directions what's going to happen at all instants of time. So it makes things a little bit more complicated, or it could make things a little bit more interesting. Okay. Isotropic medium means that you are having uniform properties in all directions. An example is vacuum. Okay, which already gives you the thought about what another material could be in terms of space. You could have anisotropic media, which means that you don't have the same value of epsilon and mu in all directions. All right. In solid state physics in your undergraduate, you may have studied about crystal structures and crystal lattice. Specifically, you must have studied about the Bravais lattice and Miller indices and all that. Okay. You must have dealt with what are known as crystalline materials, and in the crystalline materials specifically we place a lot of emphasis in the undergrad on the simple cubic system. All right. In the simple cubic system, at the corners of the cube you will be having atoms positioned, okay, atoms of a material positioned. All right. And that is one way of looking at anisotropic medium. All right. If you have a cube, the spacing between the two atoms in the horizontal direction is the same as that in the vertical direction, is the same as that in the depth or in the other inside direction, all right, depth. Right. But if you start looking at the nearest neighbor along the diagonal, face diagonal is a times square root of 2. So the atoms are further apart in the case of face, and in the case of body diagonal you will have the atoms spaced further apart as a square root 3. Now if the atoms, say you would be studying about silicon mostly in this solid state course, and you would be studying about positioning of the silicon atoms, and the silicon will have some value of permittivity and permeability. Okay. But if you start looking at these crystal structures, you will notice that the rate at which the silicon atoms will occur when you travel in the x direction, okay, will be different than what will happen in the diagonal, will be different than what will happen in the body diagonal direction, etc. So in some sense you can say that the density of the materials in different directions is going to be different. All right. Equivalently, the permittivity and permeability in different directions are also going to be different, because they are farther apart in different directions. Right. So anisotropic media are such media, right, where you have along different directions different density of atoms. Okay. So an example for anisotropic medium is crystalline materials. Okay. These are tough materials, that is you have to think about what will happen in every direction, right. And you have two more categories. You have frequency independent materials. The only example that I am aware of is vacuum. Okay. In practice, you will not have frequency independent materials, you will have frequency independence in a small range of frequencies between 1 megahertz and 2 megahertz. There is no significant change in epsilon mu or RLGC parameters. Okay. So in a small range there can be frequency independence, but in a broad range, for example, we went from 1 megahertz to 1 gigahertz, using same values of RLGC is not usually appropriate. Right. You multiplied the frequency 1000 times, you will have to recalculate what is RLGC with standard methods. Okay. So frequency independent is a good assumption for doing paper level work. Right? And to simplify math, it's a fine way to do it. Right? Then obviously you have frequency dependent. Okay. So I'm just going to put any material other than vacuum is going to have some frequency dependence. Okay. So epsilon, mu, everything is going to be frequency dependent for most materials other than vacuum itself. Right. So now you can think about small things. What do these frequency dependence mean? All these things. There can be a few questions that you can slowly start thinking about. For example, when you go to a doctor to with a broken bone and they want to take an X-ray. Okay. So the X-ray is a higher frequency, right? Or you can say that it's a different frequency than what we are used to with the eyes. We see visible, which is about 400 to 700 nanometers in wavelength. X-rays are smaller wavelengths. Right? But one could ask, why not? Why use X-rays? Right? And what is the advantage? The specific advantage in this case seems to be that the permittivity and the permeability of the skin seems to be different for visible and seems to be different for X-rays. So the visible light is not passing through the skin, okay, significantly, and we are not able to pick up scattered radiation through the eyes. But X-ray seems to penetrate through the skin. So that means that the skin has different values of permittivity and permeability for X-ray, and permittivity and permeability in visible is different for the skin. Same way for the bone. Okay. In the visible it could have some permittivity and permeability, but in the X-ray region it has a different permittivity and permeability. Right. So differences in properties are, with respect to frequency, are very useful. Okay. But they make the math a little bit more difficult, but in majority of the cases in this course we will be considering, say, frequency independent isotropic media, because that's the simplest for us to understand all the phenomena. Slowly we will introduce some anisotropy, and we will also introduce some frequency dependence. But when we are talking about anisotropy, there are many kinds of anisotropy possible. So I don't think we will have time to go through each and everything in detail, but you should have a thought that materials can be anisotropic. The way to analyze them can be slightly different. Okay. But we will see to the best whatever we can do, little bit according to paper and pen, what is convenient, we will do that. Okay. Now that we have written down the Maxwell's equations, we have written it down in the time domain, and we have also classified the media, there is one last thing that we can do before we wrap up, and that is establish the clear relevance or the clear connection to transmission line. Okay. So let's throw out del dot D and del dot B for the time being. Okay. And let's also start looking at cases where you don't have free charges. Okay. So we'll start with the simplest case. Let rho be equal to 0, that is, you don't have any free charges, there is no charge density, that means you don't have diverging electric fields, etc. You have only circular loops of electric fields. Okay. This also means that your conduction current density J becomes equal to 0, J is equal to sigma times E, alright, and here we are having rho equal to 0, so which means that you don't have charges, you will just have no conduction current. We will start with this. Okay. Okay. And I will look at only the curl equations, alright. So I am going to take the curl equation del cross E. I will write it in less detail because all the details, it depends on time, you have to use convolution, all these things now you are aware of, right. But I just want to say that I have a coupled partial differential equation, right, del cross E, which is spatial derivative dependent on time derivative of B, del cross H, which is spatial derivative dependent on time derivative of D, which is similar to your telegrapher's equations, and we will break it down in the next class and show that there is a one-to-one correspondence. Okay. But for now, let us just do this operation. We are already aware of decoupling partial differential equations. All we need to do is take del cross del cross. In the previous transmission line case, you will take dou by dou z of dou I by dou z, alright. So, the spatial derivative, the equivalent here is the operator del. So, you are using del cross E. So, this becomes minus mu del cross dou h dou t, alright. In the previous case, we would have switched the order of operators, alright. We do the same thing. Once you have dou by dou t of del cross h can be substituted from your other curl equation, right. The left hand side, however, needs a little bit of vector calculus. This is something that we have not seen in this course. There is no need. I assume that you will know a little bit of vector calculus, but I promise that you will not have any more of this vector calculus going forward, okay, because this is something that many students find it very difficult to remember over a period of extended times. Okay. So, I will just write down the expansion of the left hand side directly, okay, so that you do not have to go through the trouble of finding this. Okay. This part we have assumed it to be 0, del dot d is equal to 0. So, consequently del dot E is equal to 0. So, this is the left hand side, right. So, since the first term is 0, I have minus del square E the right hand side will become minus mu dou by dou t. Del cross h is del d del t because we have no j. Okay. We can also go one step further. If we want to get rid of d and want to express everything in terms of epsilon, we have to make some assumptions about the materials. Okay. We can make a safe assumption the material is isotropic, material is also frequency independent, in which case epsilon will become a constant. So, it will no longer be epsilon of t convolved with something, the convolution will reduce to a multiplication because epsilon is a constant. Okay. So, we make the assumption that it is an isotropic frequency independent material, then I can write this down as minus mu, okay, times epsilon alright, and the equation just says that left hand side should be equal to right hand side. So, the negative signs get cancelled out. So, I will be having del square E is equal to mu times epsilon dou square E by dou t square. It will take a little bit of time to grasp this, but what we have got is exactly the wave equation that we had from the transmission line, alright. On the left hand side you would have had dou square V by dou Z square, instead of E just put V, alright. Del, because you did not have all spatial directions there, just pick one Cartesian coordinate, dou square V by dou Z square. On the right hand side, mu will be replaced with L, epsilon will be replaced with C, LC times dou square V by dou t square. Okay. So, there is some direct equivalence going on between these Maxwell's equations and the transmission lines. Okay. So, these are not very different things. So, the theory that everything is a transmission line could actually be true. I mean, we could always look at everything as a transmission line irrespective of whether you are communicating with currents and voltages or you are communicating with simply electromagnetic fields and Maxwell's equations. In fact, all the circuit laws can be derived from Maxwell's equations. So, there is no surprise over here. Okay. So, we will stop here. In the following classes, what we will be doing is we will be going over these some concepts in detail. Just like in transmission lines, we will try to solve Maxwell's equations using computer. We will try to solve the wave equation using the computer, try to figure out boundary conditions. There we had short circuit, open circuit, all right. Here we will have equivalent conditions, all right, and then we will be having some attenuation constants, right, amplification. We had the square root of Rg coming into the picture. We will be doing all that. Once we establish the clear equivalence, right, then we will be going for the differences between this and that, which is directions, polarization, and all these topics. And then we will go to interfaces. So, I will stop here.